Prepares his laptop. I would like to introduce him as the second speaker. Amar Karkar received the Bachelor of Science degrees in Computer Engineering from Al Mustansiriya University in Iraq. I apologize for any mispronunciation. And the MSc in Information, Computer and Network Security from NYIT in Jordan. He's currently working towards the PhD degree with the School of Electrical and Electronic Engineering at Newcastle University in the UK, and his research interests include emerging interconnect technology utilization in networks on chip. Today he will talk to us about surface wave communication systems for on-chip and off-chip interconnects.
Good morning, everybody. Sorry for the delay. First, I would like to thank my co-authors, Kenneth from UCL, and Aldujaily, Alex from Newcastle University, and Kenneth from the Chinese University in Hong Kong. My paper is titled The Surface Wave Communication System for On-Chip and Off-Chip System Interconnects. First, I'm going to give an introduction about the global communication issues that are projected to scale, of the technology will scale. Then I'm going to introduce you to the new emerging technology called surface wave emerging communication system. Then we're going to propose our hybrid architecture for network on chip. And in order to accurately simulate this technology, we're going to show the analysis of link power dissipation in this communication system. And then for fully understanding of the penalty and the area overhead, we're going to show some area estimation for this proposed architecture and the preliminary results. And we finally finish with the conclusion and the future work. First, the introduction. So with continuing technology scaling, it increased and force increasing demand on the interconnect. First, when the chip-to-chip communication became relatively high, expensive in terms of performance and power, we move on to integrate, also because of the limited number of bands, we move on to integrate more devices inside the chip, their goal system on chip. And then when the bus interconnect is no longer able to handle the load required by the interconnect, the network on chip introduced. And as a projection show that this number of nodes and devices need to be interconnected inside the chip will increase, the global communication issue is going to introduce, and it will suffer from high power consumption and low performance, delay, and so on. And ITRS and many studies has covered this area in more details. So this inspired many studies to look for alternative fabric to handle these issues. Here we come on surface wave. So why surface wave from all the rest of alternative fabric? Well, in general, let me first say what is a surface wave interconnect. Xenic surface wave is an electromagnetic signal that propagates between an interface between two different medias, and the surface, which is the surface, and this surface is corrugated, and its dimension is specifically designed to achieve a specific impedance. So this electromagnetic wave will propagate, as we can see here in the figure, smoothly with a low power dissipation. In general, radio frequency interconnect have a lower implementation cost because it doesn't need non-CMOS technology to be integrated inside or outside the chip on such the optical fabric, optical interconnect, sorry, and doesn't face that much industrial challenges such as for the 3D, such as heat, low wave, thin wave, and so on. So radio frequency interconnect can be classified into two types. The first type is wireless radio frequency interconnect, which dissipate more power as the signal is propagating in free space. And the second type is transmission line waveguided, that this modulated signal move in wires that expensive, let's say, wire that need extra die area and deliver the signal only to the nodes that these wires pass through them or by them. So surface wave combine the best features of these two types of radio frequency interconnect, as we will see. So in order to have a clear image about how this technology can be implemented for network on chip, we figure out the best option is to implement it off the chip. This way it will have three advantages. And the first one, this way it will be able to use for intra-chip communication. And the second one, it lower the implementation cost, and no need for extra die area for this surface to be implemented in the upper layer. And third, it offer much better propagation speed for the signal, since the electromagnetic signal is inversely proportional to the permittivity and permeability of the electronic of the media transmitting these signals. So here we will have the air, the surrounded air of the surface as the dielectronic, which is have a better feature than the rest of material used for dielectronic. So also we need to integrate a transceiver, and many studies are state-of-the-art, proposed state-of-the-art transceivers, integrated transceivers, and it's well known, and you have it in all your mobile devices. We adopted the one proposed by Chang in 2011, which is a transceiver used for wave-guided signals. Also, we need to implement a vertical diode that can be realized through by the technology through silicon via to achieve the right launching of the signal to the surface. And the structure of this transceiver, as you can see here, based on FDMA modulation, and we choose to have these 128 sub-channel in order to achieve transmission of one flit per cycle. Of course, you can have less number of these orthogonal sub-channels to reduce the area overhead, but We are targeting here performance critical systems. So we're gonna go on with our consideration for this number of sub-channels, as you can see here. So the hybrid architecture. Even though surface wave has all these features, it still has this inherited limitation from radio frequency interconnect, which we still depend on this shared media and limited number of channels, and resulted from a limited range of frequency, and therefore, and moreover, local wire seems to scale well with the technology, because of the devices getting smaller, the local communication, the wires also getting the distances is smaller. So the projection show there will be no problem with the local communication for wire, and therefore he is still the cheapest interconnect media for local communication. So we are proposing that we use a hybrid architecture that combine both these technologies. The first layer, as you can see, is a regular mesh. Here in our example, we have 4x4 network, and the second layer is the radio frequency surface wave interconnect. And here in our example, we have two nodes that have the capability of TX, RX. We're going to call them master nodes. And the rest of the nodes have only implementing the receiver in them. We're going to call them the slave nodes. Of course, here in our paper, we do not do any optimization algorithm to locate the position of these master nodes. We just fairly distribute them through the network to observe, to have a first look about how what this technology have to offer for network on chip. So keep that in mind when we will see the results. So in order to accurately simulate the power consumption and the power dissipated by this technology, we have an experiment results for a range of frequency, as you can see here, for different distances. Since the surface wave is electromagnetic wave that propagates through this wave guide media, the transmission line model fit perfectly. And therefore we use the equation number 1 where we can calculate the voltage magnitude, and it's inversely proportional with the attenuation constant and the distance. Alpha is the attenuation constant and D is the distance. And then we can calculate S21, the voltage gain. Here we have E is the loss resulted from the inefficiency of launching the signal between transducer and the surface due to the use of off-shelf lab equipment. So we use these results and implement them in the MATLAB fitting tool to obtain the value of alpha and E. And we draw this calculated based on the values we obtain for alpha and E, which we will use in our simulation, which is fairly close with the minimum error rate, around 2–3%. So in order to have a better look, we need to know how this technology is going to be area, Hungary or not, or comparing with related work that perform the same or offer us the same performance result. So we use the Orion network on chip area simulator, and we depend on the baseline, the specification of baseline architecture, which is the single cloud computing chip. And we use them to calculate the extra area for the 6-port. As you know, we have 4 port for the 4 direction in each router, and 5th for the local, and now we have the 6 for the second layer of our architecture, which is the same here with the radio frequency transmission line based model, the same area. However, regarding radio frequency circuit and links, here we have a slightly extra area needed by radio frequency interconnect transmission lines due to the need to implement these transmission lines and the repeaters to propagate the signal and so on. And when we compare for the single cloud computing, we that implemented in 45 nanometer technology, and with the calculation of the frequency range that we have for this technology and the switching speed for transistor, we consider that we can implement 6 channels, so with 6 master nodes and the rest of them is receivers. We calculate that the total die area, extra die area needed is around 2.29 for the whole die area, which is around 560 millimeter, which is less than the radio frequency interconnect transmission line. Primary result here we show the comparison between our architecture and the baseline architecture. And as you can see, we have significant advantage in terms of average delay and throughput as the bit injection rate is increased. Our architecture show higher performance. And here is a comparison for different type of traffics. As you, the average for most of these traffic is the improvement average is around 35%, and these results are obtained on the edge of network saturation, where the network reaches double the zero latency. So in terms of performance, the hybrid architecture show better better result, which is due to the fact that packets are no longer need to travel through these expensive and congested wires and routers. It can take this shortcut to the through the surface wave to its destination. And here is the normalized power results to the baseline architecture, and for different network size and different type of traffic. Which, as you can see, in most cases, the saving is start to increase as we increase the size of the network, which is a proof that as the global communication issue is increased, our architecture have more to contribute to the power saving and performance. So, conclusion and the future work. We presented the scalability issues, projected scalability issues, and in terms of global communication, in terms of performance and power. We propose the hybrid architecture enabled by surface wave as a supplementary interconnect for metal wire. Significant potential for this proposed architecture are shown through the simulation. And this is an ongoing project that future work will include work on optimization algorithm for positioning these links in design time or in runtime. Also, this fabric will have much to offer for one-to-many and many-to-one traffic patterns. So thank you very much for listening, and any question?
Questions?
10 to the power minus 14, and this gives us, according to single to noise ratio figure that we need to achieve at all times. And if we achieve this signal to noise ratio figure, we'll have a bit error rate higher than this targeted, let's say, low bit error rate. And therefore, according to this, we calculate how the range of the signal and how much signal to noise ratio it needs to be. Did I answer your question? Or?
I guess partially, at least.
Well, I think the answer was more like a method rather than the realistic sort of figures.
Because I was wondering what kind of distances and data rates you would end up with that error rate.
Well, we have, according to our calculations, we have up to 15 centimeters. Will be with minimum bit error rate. The details you can, of course, in the paper are provided.
Do we have any more questions? I actually have one. Also, it's, I guess, a bit of a clarification question. When you initially showed that you would like to transfer a whole fleet of 128 bits, the assumption is that you would need 128 modulating frequencies, so each bit is modulated
by sub-channel, so that orthogonal sub-channel, and this way, and then they combined and transmitted.
So if you have, as you said, more than one transmitter, let's say 6, I think you mentioned 6 for a big chip, you would need 6 times 128 such sub-channels.
This is why we are taking, for example, in our simulation, only 6 channels, each channel with 128 sub-channel, because we're giving the range for 45 nanomillimeter. We have taken the range from 20 to 100 gigahertz, something with the channel bandwidth required and channel spacing needed.
So you wouldn't have interference. And you modeled that in your simulations, the interference when multiple transmitters are sending.
Well, this is multi-group work. So the other group that work on the communication part, let's say, modeled that and actually done the experiment. In our simulation, we've done a system-level simulation that model how this can affect the overall performance of network on chip.
Okay. Thank you very much.
Thank you.